If we have a process where we're producing parts that are supposed to be equal, part 1, part 2, part 3, for example, when we measure them or take multiple measurements on the same part, we will commonly get a difference in the measurement. So we take two different measurements of, say, part number 5, and it's very common I'll get two different measurements from that same part. And also, it is common that I will get different measurements between different parts. So while I might get 5.3 and 5.6 units, whatever this is, on part 1, I should expect to get the same kind of measurement on part 2 and 3, but you'll notice over here on part 4, for example, I get 6.1 and 5.9. So I have both within part variation and between part variation. So that is part of the measurement system. More specifically, though, I have both in any given process, I've got both part-to-part variation and I've got measurement system variation as well. Now, what I'm going to try and do in this module, or what we're trying to do in the project actually, is we're trying to eliminate variation due to the measurement system. And then if and when we've got part-to-part variation, we need to deal with that. But the whole point of MSA is to eliminate or at least minimize measurement system error. And as we saw in the module, of course, there's two components to that. One is accuracy, dealing with gauge calibration, and then there's the precision itself. Now, looking just at the precision, we've got three components, but the two I want to talk about are repeatability. So this is the ability of a given operator under a given set of conditions to be able to get a consistent result. So while we're looking for, from the same person, we're looking for maybe a pass in all of these, but yet one we get a failure. That would be our ability or our inability to repeat. And the way you kind of fix that perhaps is maybe through employee training or introducing some sort of a standard. It could be equipment related, but in terms of the repeatability, assuming that the equipment is correct or adequate or operational or operating, then it's probably a person's skill level or experience level or some other mechanism like that. It could be the lighting, it could be the position from which they're observing, and that kind of thing. On the reproducibility side, the issue we have is, can different operators under different conditions who are expected to get the same result, can they get the same result? So while they're all looking at a given part, we would expect them to get all of the same results. So pass, but in this case fail. So we don't have an ability here to reproduce. And again, that might be employee training, or it might be an SOP or something along those lines. So let's be clear that while when we get an MSA to pass, and I might have mentioned in an earlier video that an MSA is considered a project within a project, because lots of times in your project you're going to find that even though we, the organization, or we, the leadership, have some notional knowledge or anecdotal knowledge that a process is broken or needs repair or the defect level is too high, it's not that common to have an accurate measurement system that's telling them that. In some cases that's true, but in many, many cases it's not true. And so the team will get locked on the MSA because what they're going to find is the measurement system isn't adequately representing the behavior of the process as it was intended. However, when we do get an MSA to pass, just know that it means we can get the same answer under different conditions using different people, right? So I've accomplished repeatability, I've accomplished reproducibility, but it doesn't mean that the answer is correct. And of course, what this statement is alluding to is that it assumes the gauge has been adequately calibrated, and that may not be true. So while the MSA, at least in the context of this training, we don't address gauge calibration, it's not something to overlook. There is a high probability that you've got people in your organization who do set up gauges and look after gauge calibration. Now, just moving on, I want to look at the attribute MSA just briefly. So in terms of the mechanics of it, we want about 30 samples. More is better, of course. I have seen templates out there that go up to about 50, but 30 is certainly adequate. So we identify that you need to uniquely identify each sample and number them, and then make some assessment as to whether or not, say, they pass or fail. And then as the appraisers come in to make their assessment, what we want, appraiser 1 during trial 1 on part 1, what we want them to do is give their assessment as to whether it passes or fails, and we would record that here. And then on to sample 2, appraiser 1, on to sample 2, and on to sample 3, and so forth. Then we bring in appraiser number 2, and we go back and start at trial 1 for appraiser number 2, and we would have them assess part number 1 and part number 2 and part number 3 and so forth. And then appraiser number 3 would come in and they would give their assessment, and these are recorded again here. When that's all finished, then we come back to appraiser number 1 and we execute a second trial. Now, at least in theory, we want to randomize these. So the parts have been uniquely identified, 1 through 30. The appraisers can't see that, and so we want to randomize the order within which they are presented to the appraiser for trial 2, and the same for appraiser number 2, trial 2, and so forth. And once we get trial 2 completed, then we come back for appraiser number 1 and we execute trial number 3, again randomly ordering the 30 samples that we have. So that is really quite important when we're trying to get an evaluation from each of the appraisers for the 30 samples. Now, just kind of moving on to the variable MSA, the same kind of thing. In this case, though, we only need 10 samples. 10 samples is adequate. And we've got appraiser number 1 here. And in the same manner as we had the attribute data, we've got trial number 1, and the measurement is given for trial number 1. And then you would bring in appraiser number 2, and they would execute trial number 1, and so forth. In fact, you can see that here, although the clarity is not, or the resolution is not great, you can see here this is appraiser 1, this is appraiser 2, and appraiser 3, this is trial 1. So we would have appraiser 1 assess 10 samples for trial 1, and then we would bring in appraiser 2 for trial 1 and record the results, and then bring in appraiser 3 for trial 1, and then we would go back all the way back to appraiser 1, change the order of the samples that are presented to appraiser 1, and execute trial number 2, and then have appraiser 2 come in and so forth and execute trial number 2. So the randomization of the samples as presented is important, and also the trials themselves have to be separated with some time, and that can only be dictated by the measurement itself. So it doesn't have to be any extended period of time, but we want to break up the samples and the not only the order that they're presented to the appraiser, but also between each appraiser's trial. We want to make sure that there's some time between each of the trials. And that is an overview of MSA, an extremely important part of projects, but just be cautioned that it can be a lengthy part of the project itself, and that's why we call the MSA a project within a project, because it literally, teams can stay at the MSA part of the project for weeks and even several months. But I would say that because MSA is critical, the extent to which we are able to accurately measure a process and the process output, the big Y, the MSA must be completed and the measurement system must be fixed before we can move on to other parts of the project.